So of course, one of the biggest questions we can ask now we've discovered exoplanets is, are any of them able to host life? And indeed, do any of them actually host life? So wrapped up in that is the concept of habitable zone, which you might have heard. So really, we don't know much about the possible forms of life that could exist, but the first sort of position we have to do is to try to find life that might exist that's like us, essentially, like that we find on the Earth. It's the only evidence of any sort of life we have currently. So a habitable zone is a way to try to sort of simply capture that and decide in advance whether a planet could possibly host life. That's what the habitable zone is telling you. Could this planet possibly host life like our own? So the habitable zone is quite a simple concept. If we have our not to scale planet and on our star, essentially as we get closer and closer to the star, we'll get hotter and hotter, of course. And you can imagine that water in particular might be boiled off and removed from the atmosphere. If we get further and further away, that water might condense and freeze out. And it's really water that holds the key, because life as we know it in most cases really relies on the presence of liquid water in our bodies to sort of transport both materials and resources, but also information as well. So the habitable zone is a very simple calculation to say, do we expect this planet to be able to host or have liquid water on its surface? And as I've just said, if it gets too close, it'll be too hot, the water will be evaporated. If it gets too far away, it will be frozen out. But it's a little bit more complicated than that. Unfortunately, and it's complicated by atmospheres. We know in our own solar system, for example, Venus, Earth and Mars, the kind of trio of terrestrial planets, they're not that different actually. They're not hugely different in terms of size or distance from the Sun. But actually, you might expect, if you did a naive calculation, let's say Mars, Venus, Earth were detected as an exoplanet trio, a very simple calculation, we might initially expect them all to be habitable, all to have liquid water on the surface, or at least be able to have it. But if we look at Venus and Mars, they're very, very different to Earth. Venus is far too hot, the temperatures are 500-600 degrees C, and it's believed that most of the water has been evaporated away, or almost all of it. Whereas in Mars's case, obviously there's recent announcements of the possibly evidence of liquid water in the past, but at the moment it's far too cold and it's locked away, probably under the poles of the planet as ice. So what's happened there, or the difference at least, there's a lot that we don't understand about those three planets or the way they're connected. But what's happened is that Venus essentially at the moment has a much thicker atmosphere. That atmosphere is like a big blanket that keeps it too warm in a sense. Whereas Mars has a much thinner atmosphere and it can't keep as warm and it's much cooler, and then the water is essentially frozen out. So the key point is that habitable zones are just an attempt to do a simple calculation about whether water might exist in its liquid form. And that is simply a guide to us to say, well, could it support life like us, life like we find in our biosphere? But it's important to remember at this point that the term habitable zone is just a kind of simple first order calculation, and we really need to understand the atmospheres of these planets if we are going to know if they are indeed habitable. And that's why we need to use observations, things like transmission spectroscopy eventually for these objects, for more Earth-like planets, and also be able to use models to interpret the conditions. So we've spoken a bit about habitable zones and where we might expect to find life, but of course the real big answer is, could we ever prove that life exists on other planets? And for that, the key term is a phrase called a biosignature. So it's quite a simple word, just a signature of biological life, a biosignature. And to do that, yet again, atmospheres are absolutely key, our understanding of atmospheres and our ability to observe them. So we know that on Earth, if we were to take a test tube of the Earth's atmosphere and sort of seal it away, the balance between the gases would change. That sort of test tube of gas would react with itself in a sense until it got into balance, because the Earth's atmosphere is currently out of balance. It's not in any sort of what we would call equilibrium, and it's being driven out of equilibrium by various mechanisms, and quite a few are based around biology, life, emitting and respirating, breathing in, breathing out, etc. So what we really mean when we're trying to search for life in planets other than the ones in our solar system, where the search is slightly different, where we're looking for fossilized remains or maybe microbial life, when we look to exoplanets, we're trying to find the indirect effect of life on the atmosphere, what a sort of astrophysicist would call chemical disequilibrium. So to do that, we use some of the techniques like or we will use some of the techniques like transmission spectroscopy to work out which species we can see in the atmosphere and then whether they're in balance or they're out of balance.
Well, we can't actually yet look for biosignatures on extrasolar planets. And there's a couple of reasons for that. One, the planets that we study just aren't really favorable to look at that and study their atmospheres. So we're looking, quite extensively at planets like hot Jupiters, but to scale, something the size of the Earth is much, much smaller. And the signals are much, much too small to actually detect. And also the telescopes we have just quite aren't up for the job yet. So telescopes like the Hubble telescope are wonderful instruments and can tell us a lot about planetary atmospheres. But the planets we might start to look at for biosignatures are just too far away. And Hubble is just not quite big enough to do the job. But the exciting thing about extrasolar planets is this is all coming very soon. So in only a little over a year and a half from now, the James Webb Telescope will be launched. And there, the first searches for biosignatures will probably start. And what that will do is look around planets transiting small stars. So you can imagine, we have our hot Jupiter. Well, this is pretty favorable because the size of the planet isn't so different than the size of the actual star. So in order to boost this signal, what you can do is you can look around smaller stars. So now the planet, in comparison, looks much bigger. And then when you look at something the Earth's size, you can actually detect that because now you've scaled down the planet and the contrast for it's scaled down the star, sorry, and the contrast for the planet will look larger. So with James Webb, the searching around such rocky planets around small stars will start. And then in the not too distant future, maybe a couple of decades away, very large space-based telescopes could use direct imaging to then tease out, say, the pale blue dot around a more normal size, a larger star.
Now, the warning signal with this is that, unfortunately, there are lots of sort of physical or natural processes that can mimic that. So we really have a lot of work on our hands to try and understand biosignatures, if you like, and which are definitely linked to biology and which aren't. For example, volcanoes can drive an atmosphere, or sort of that sort of activity can drive an atmosphere out of balance. So when we detect the first biosignatures, which hopefully we will do at some point, there will still be a lot of work to understand and determine if they're definite proof that life exists on a given planet.